models. And the presenter here is Martin Knocker, who works for MCI.
Hello, my name is Martin Knocker, and I present our paper HEMAN, Homomorphically Encrypted Machine Learning with oNnx models. This is joint work with David Drexel, Michael Rader, Alessio Montoro, and Pascal Schöttler. So machine learning services are becoming increasingly powerful and are used in a variety of applications. As an example, we will look at a neural network to classify handwritten digits. The output is determined by the output class with the highest probability. Today, such services are commonly hosted by machine learning service providers that enable easy access and utilization of these services for clients. However, if client data or the model are private information, no party wants to hand over the sensitive information to each other, such that no party can benefit from each other. To protect the privacy of both, we could use cryptography. However, classical crypto systems only protect data while being transmitted or stored. This means that clients can encrypt their data, transmit it to a server. However, before evaluation, a server has to decrypt the data again. Similar holds for returning the result. This has the obvious problem that a server has data in the clear text. To overcome this, we could ask the server to perform the evaluation on the encrypted input. However, with classical crypto systems, this results in garbage output after decryption. And this holds not only for machine learning models. A solution to this is homomorphic encryption, which allows for computations on encrypted data. As an easy example, we have two numbers and we ask a server to compute the sum of both. However, we don't want the server to have access to the plaintext data. So we homomorphically encrypt our numbers and send it to a server. The server is now able to perform the operation on the encrypted inputs. The result is still an encrypted ciphertext, which is returned and decrypted by the client to receive the final result. The server never has plaintext information about the inputs or the result. If a homomorphic encryption system supports both additions and multiplications, it is termed a fully homomorphic encryption system, or FHE in short. So why don't we always use FHE instead of classical crypto systems? In an ideal world, we could use FHE with perfect security, high accuracy, and high efficiency. However, in the real world, there is always a trade-off between these. For example, a high accuracy comes at the cost of reduced efficiency. Additional challenges are that FHE operations are orders of magnitude more complex in terms of runtime compared to plaintext operations, and a reduced operator set, which means that only additions and multiplications of ciphertext are possible. So how does this help in our initial example? Clients can encrypt their information, send it to a server, who is now able to perform the computation on the encrypted input. The result is still encrypted and returned to the client, who can decrypt to receive the final result. The advantage is clearly visible. A server never holds clear text data. And this is what we implemented in our tool HEMAN. Model owners provide their models and receive a reward in return, and data owners provide their inputs in an encrypted form and receive an encrypted result that can be decrypted to receive the final result. Neither party has information in the plaintext about the other party, and in the following we will focus on the model owner's model, who is supported in the oNnx format in HEMAN. Previous work only implemented the FHE inference of specific neural networks, which means that the inference phase was hard-coded for these specific neural networks, or that only individual machine learning frameworks were supported. So therefore we use the oNnx format in HEMAN, which gives us a well-defined format definition, but more important, we are independent of the underlying deep learning framework that the model was trained with, and that oNnx is supported by most programming languages. So how is this implemented in He-Man? So far, we implemented the most important operators of the oNnx operator set. This is done by implementing an equivalent of the operators for FHE ciphertext, which can be quite tricky because of the mentioned restrictions. During the FHE inference phase, data is passed through the operators, and each operator uses the FHE equivalent implementation. We evaluated our tool by measuring the performance in terms of classification accuracy and latency of two applications. First, a handwritten digit classification using the MNIST dataset, and second, a face recognition task where we use the LFW dataset. I won't go into the details of the numbers, so I just tell you the key result, namely that we achieve accuracies that are almost on par with the baseline accuracies. However, this comes at an increased runtime. But we achieve inference with same accuracy while preserving the privacy of the data and the model. So to conclude, we introduced He-Man, a neural network inference tool on homomorphically encrypted data that preserves the privacy of the data and the model. We achieve accuracies close to the plaintext values and support a broad range of models via the oNnx format. Future work targets the full oNnx operator set implementation to support even more neural networks. So thank you for your attention, and I invite you to visit our code repositories or read the full paper. Thank you very much.
Thank you, Martin. I believe Martin is online, so he can take any questions from the audience. Yeah, Hester. The question is, are there, on the operators you've re-implemented, are there precision constraints that they only take FE32, or can they take other precision formats?
Thank you for your question. So far, we implemented float 32 precision. This is because some operators are restricted for float 32, so we support these.
I was wondering what's the backend, hardware backend for the latency measurement? If the backend is CPU, can we accelerate this process using GPU and reach minimum latency loss?
The question was for your latency measurements?
Thank you, I already understood. That's a really good question. So far, there are only really few FHE libraries that support GPU support, and these are proprietary libraries that are not open source. And as we use open source libraries, this is a cheap CPU measurement. However, there is much effort going on into providing GPU support for major open source libraries.
Yes.
Given how only add and multiplier supported, how do you do the normalization softmax?
The question is, given that with FHE you only support add and multiplication, how do you do normalization? How did you re-implement the normalization operator using these operations?
Thank you very much. Yeah, actually, so softmax is not supported currently, but what we do is a ReLU as a first step. And in general, every nonlinearity is approximated by polynomials. So there is a trade-off between how large you take the degree of your polynomial, which improves your accuracy. However, the higher the degree, the more multiplications you have to do, and the longer it will take for your computation. So there is this trade-off. And basically every linearity is approximated by a polynomial.
Okay, thank you. Any more questions?
I have one. Have you talked to anyone in the ONNX community around how to contribute these for broader adoption, the operator implementations that you have?
No, actually not. So for us, it was just a feature that we support a large range of pre-trained models, but haven't talked to ONNX members or community members. So that would be really interesting to do. Yes, so happy to do that.
And what would you suggest the avenue for introducing this, like turning up in the operator SIG?
Yeah, I think we should take it and have a discussion around with the operator SIG. We meet quite often, once every couple of weeks. So Michael Karzinski can help you on that front, or Rama.
Great, so just send me an email. Thanks.
They should be on the bridge right now too, if you want to talk to them.
Great, thank you very much.